China's record-breaking 18-minute stable plasma announcement had barely settled when on January 10, a groundbreaking discovery was announced by an international team led by researchers from the University of Seville. One of the biggest challenges in fusion energy has been the sudden and unpredictable bursts occurring at the plasma's edge. Until now, scientists had struggled to understand why these instabilities happened. But that mystery has finally been solved. The researchers claim they have uncovered the nature of these erratic plasma bursts and, more importantly, discovered how to control them. This breakthrough marks one of the most significant steps toward achieving long-term stable fusion energy. In other words, a massive leap toward unlimited clean and safe power. While Europe and China push forward in the race for fusion energy, Trump and tech strategist Elon Musk continue to double down on fossil fuels, slashing scientific research budgets under the motto. But science doesn't stop. Europe and China continue making massive strides toward an infinite energy future. The researchers from the University of Seville have published their groundbreaking discovery in Nature Physics, a highly respected peer-reviewed journal. If you want to dive deeper into the details of this revolutionary study, we've left the link in the description. You're probably familiar with solar flares, massive energy eruptions on the sun's surface. Well, fusion reactors face a similar issue. At the plasma's edge, just like on the sun, completely unpredictable bursts occur, preventing stable and sustained energy production. So far, the longest stable plasma ever achieved was sustained for 18 minutes at China's East Fusion Reactor. However, for commercial energy production, this duration needs to be significantly longer. The only way to achieve this is by understanding the nature of edge instabilities and using magnetic fields to control them accordingly. And as of January 2025, European scientists seem to have identified the root cause of this issue. But how exactly do these reactors hold the potential to generate massive amounts of energy? Fusion reactors mimic the sun's energy production process by forcing hydrogen atoms to merge under extreme heat and pressure. This reaction releases an enormous amount of energy. In fact, we all encountered this concept, at least briefly, during high school. Does E equals mc squared sound familiar? I know, whenever we hear this formula, we think, here we go again with this guy. But let's be honest, Einstein was truly one of the greatest scientific minds of all time. To grasp the sheer magnitude of energy involved, let's break it down with an example. When deuterium and tritium nuclei fuse, they form helium and a neutron. The total mass of the resulting helium and neutron is slightly less than the initial hydrogen isotopes. That missing mass is converted directly into pure energy, according to E equals mc squared. And just to clarify, c, the speed of light, is approximately 299,000 kilometers per second. As a result, just 1 gram of fusion fuel can generate around 100 megawatt-hours of energy, equivalent to roughly 10,400 liters of gasoline. Of course, the most important question that comes to mind here is, how much net energy is actually being produced? In other words, how does the energy required to create the plasma compare to the energy generated from the reaction? Let's be upfront, as of now, no fusion reactor has achieved sustained net energy production within a commercially viable time frame. But we'll get into that in a moment. If you can recreate the extreme heat and pressure found inside the sun and force hydrogen atoms to fuse here on Earth, nature offers you an almost limitless energy source. But wait a minute, aren't we basically talking about creating a star on Earth? Wouldn't that be dangerous? Fusion energy does mimic the sun's power generation, but fusion reactors on Earth work completely differently and, according to experts, do not pose a major risk. The key reason is that unlike in the sun, artificial fusion on Earth is not a self-sustaining process. In nuclear power plants, once a reaction starts, it can continue uncontrollably, leading to catastrophic chain reactions if something goes wrong. However, in fusion reactors, if the magnetic fields confining the plasma fail, the plasma cools down instantly, and the reaction stops automatically. Additionally, fusion reactors do not produce long-lived radioactive waste, unlike nuclear fission reactors. At least, that's what scientists claim. Of course, as with any advanced technology, there is always a risk of accidents. However, even in the worst-case scenario, a fusion reactor failure would not cause a global-scale disaster like Chernobyl. Its effects would be strictly local. To fully grasp the significance of the breakthrough made by scientists in Seville, we first need to take a closer look at how a fusion reactor actually works. The basic principle is simple. At extremely high temperatures and pressures, hydrogen isotopes fuse, releasing an enormous amount of energy. But just how high are these temperatures? So far, the highest temperature ever recorded in a fusion reactor was achieved at China's East Tokamak, reaching 120 million degrees Celsius and maintaining it for 18 minutes. In the Western world, Korea's superconducting Tokamak Advanced Research Reactor reached 100 million degrees, but only sustained it for 30 seconds. These numbers demonstrate just how far China has advanced in fusion research. But how much trust you place in these records is entirely up to you. One of the biggest questions that comes up is this: what kind of material can withstand 100 million degrees? Wouldn't everything just melt? There are actually two answers to this. First, fusion reactors never allow plasma to come into direct contact with the reactor walls. The temperatures inside are simply too extreme for any known material to handle. Instead, powerful magnetic fields are used to keep the plasma suspended, preventing it from touching the walls. However, no matter how strong the magnetic fields are, the reactor walls still experience intense heat and neutron bombardment, creating a major durability challenge. This is where the second answer comes in. Even though plasma is kept away from the walls, the reactor still requires the most heat-resistant materials on Earth. That's why tungsten and tungsten-based compounds are used. These materials are among the most heat-resistant substances known to science. At this point, it's worth mentioning what's needed for both magnetic field control and advanced material discovery: extremely complex calculations, highly skilled researchers, and supercomputers capable of handling massive simulations. And if we take it even further, without expertise in quantum computing, quantum algorithms, and advanced physics, conducting this kind of research is nearly impossible. Magnetic fields are used to control this extremely hot plasma. Until now, it was well known that plasma stability was most frequently disrupted at its edges, near the reactor walls. However, the exact nature of this instability remained a mystery. Without solving this issue, commercial fusion energy would be impossible. But now, scientists from the University of Seville claim they have cracked the code. In their own words, "We have unlocked the secret to stable fusion energy." Quoting directly from their paper, one of the biggest challenges in fusion reactors has been edge instabilities in the plasma. Until now, the exact cause of these instabilities was unknown. However, our experiments and simulations have revealed a key finding. Due to high temperatures, energetic ions, fast-moving, electrically charged particles inevitably form. These energetic ions directly trigger edge instabilities. In fact, we have discovered a strong correlation between these unpredictable plasma bursts and the presence of energetic ions. To put it into simpler terms, if energetic ions can be properly controlled using magnetic fields, these bursts can be significantly reduced, allowing the plasma to remain stable for much longer. In other words, one of the biggest barriers to sustained fusion energy may have finally been removed. Wow, this is truly mind-blowing. If the findings of this research are successfully implemented, we may soon hear about a record-breaking breakthrough in fusion energy coming from Europe. To truly grasp the significance of this discovery, let's take a closer look at how this research was conducted and why it matters so much. This study's measurements were conducted at the Aztecs Upgrade Tokamak, located at the Max Planck Institute for Plasma Physics in Garching, Germany. Simulations were carried out using MEGA, a hybrid code specifically developed to model the self-consistent interaction between edge instabilities and energetic particles, making it the first simulation model capable of such calculations. Earlier in the video, we mentioned that we'd return to the net energy question. In fusion research, net energy gain is measured using the Q factor. Simply put, how much energy is spent to sustain the plasma, and how much energy is generated as a result. If you put in 1 unit of energy and only get 0.7 back, the process is not viable for commercial use. But if you put in 1 and get 10, then fusion energy truly becomes a revolutionary power source, one that is also completely clean and sustainable. This is why having a stable Q factor well above 1 is absolutely essential for a practical fusion reactor. China's East reactor reported an 18-minute plasma stability record, but did not disclose its Q value. Previously, East had reported a Q value of 0.4. However, when we couldn't find any updated Q value for East's latest record, we specifically asked DeepSeek about it. Their response was interesting. They claimed that for now, the focus is on sustaining plasma duration rather than Q values, suggesting that at this stage, it is not the most relevant factor. They did, however, provide us with their theoretical target from a Chinese research report, a Q value of 50, meaning an energy output 50 times greater than the input. Today, we took a deep dive into the latest advancements in fusion energy. We'll continue following these developments closely. See you in the next video.